So, hi and welcome everyone, and thank you for joining us for this Cambridge University Press webinar. My name is Ellie Pawsey, a marketing executive with Cambridge University Press, and it's my pleasure to introduce Colin Anderson to discuss his new textbook, Wind Turbines Theory and Practice, published in February 2020, and guest speaker David Quarton. Colin has spent over 35 years in wind energy, beginning as a research engineer and later working for a turbine blade manufacturer. Since 2004, Colin has been a consultant to a number of industrial and community-based wind energy projects, and he currently teaches a master's course on wind energy at Edinburgh University. David began his career working with a wind turbine manufacturer, after which he spent almost 30 years at an engineering consultancy and became a director responsible for wind turbine engineering services and software development. David is currently a visiting professor at the University of Bristol, where he teaches a wind and marine power module. The course uses Colin's book as a standard reference text. Now, just a few housekeeping points before we start. You have all joined in listen-only mode. However, you can submit questions throughout the event in the Q&A box. We encourage you all to do so, and Colin and David will answer as many as they can after their presentation. The webinar will begin with a short presentation, followed by the Q&A section. And a recording of the event will be emailed to you afterwards, along with a link where you can find out more about wind turbines theory and practice and request an examination copy. We hope that you enjoy this webinar, and without further ado, I will hand you over to our panelists. Over to you, Colin and David.
Thank you. Thanks very much, Ellie. And I'd like to thank you, Ellie, first off, and everyone at Cambridge for putting this webinar together for us. It's a great opportunity. And I'm delighted that David is able to join me today. What we thought we would do is choose a few topics in wind energy that are current and maybe some of them not so current. And I will, in some cases, try to explain how I've addressed these in the textbook. Or in some cases, maybe they haven't been addressed in the textbook. But David, who I've known for, I think, over 30 years in the wind energy field, is an authority in many aspects of wind energy, and I'm looking forward to the opportunity to discuss some of these topics with him. We'll talk for maybe about 15 minutes and then turn over to a Q&A so that the guests can fire in questions. And what we've done is David and I have chosen just a few slides based on some topics that illustrate some modern aspects of wind energy. So we'll put those up, and each of them kind of poses a question which we will attempt to answer. So if you're ready to go, David, then
Absolutely.
I shall
Yep.
put up the first slide. This is an image that I've chosen. This is to illustrate the topic of wind turbine wakes, which I've addressed in a couple of places in the book in terms of aerodynamics and structural fatigue. But what the slide illustrates is that the photograph shows 3 turbines in a linear array, and measurements from the second turbine. The second turbine is sitting in the wake of the first one when the wind is in the direction shown. And the graphs on the right show the effect on the wind velocity at the second turbine, the wake affected turbine. The top graph shows the wake velocity as a fraction of the free stream velocity. The lower graph shows the turbulence experienced by that second turbine. And these two quantities, the wake velocity and turbulence, are very much determined by the conditions at the upstream wind turbine. And it depends on the wind speed, but the thing it depends most on is the thrust coefficient of the upstream turbine. And this graph here shows how the wake deficit actually gets deeper, not in high winds, but at high tip speed ratio. Now, I know, David, you were heavily involved in research on wakes way back in the early days.
Yeah,
absolutely. I think it was in an experiment, something like this, that we first came across each other.
I think it probably was. I think it probably was, yes. Yeah, that's right.
If you would like to say a bit about turbulence, because I think that's an area that you you have some.
So, yeah, that's right. I want to focus a little bit on the lower graphic there, which shows you how the turbulence varies across the wake. So clearly, the turbulence intensity is at its peak in the middle of the wake, as you would expect, and then it decays back to the ambient level at the edges of the wake. Conventionally, we think about the wake turbulence being made up of two components, actually, the ambient turbulence and another component we call the added turbulence. And the added turbulence really is the turbulence which is introduced to the atmosphere by the rotor wake. So those two components join together and give us the overall wake turbulence. And as Colin already mentioned, the wake turbulence is actually dependent on thrust coefficient. So you see there in that graphic at the lower wind speed where the thrust coefficient is higher, the turbulence intensity is higher. And then as the wind speed increases, the turbulence intensity goes down. The turbulence in the wake is really important from the point of view of the fatigue loading on the downstream turbine. So we need to understand how that turbulence develops as the wake moves downstream from the rotor. And one of my very first research projects when I got involved in wind energy back in the 80s was to bring together about 100 experimental data sets, some of them from wind tunnel tests, some of them from real wind turbines in the field, and pull together the turbulence intensity measurements that were made in a wake situation and try and make sense of them. And what I did at the end of all that work actually was to pull together a kind of empirical characterization of the wake turbulence. And the formula that came out of that empirical characterization actually is in Colin's book. And it shows you that the wake turbulence is dependent on three parameters. It's dependent on the thrust coefficient, it's dependent on the ambient turbulence level, and it's also dependent on the distance downstream of the rotor. So that empirical formula actually is still used quite widely in the industry to characterize turbulence within a wind farm. A very similar formula has made its way into the international design standard for wind turbines. So quite an interesting first project, really.
Sorry, just going to interrupt you very quickly. There's a couple of questions have come in, which I'm trying to type some answers to as we go on. Actually, I don't need to type them. I can speak them.
You speak them.
Just to explain, in the diagrams, U is the free stream wind speed. It's the undisturbed wind speed, which in this case is measured at the upstream wind turbine. It's slightly corrected by the controller, but it's basically U is the free stream wind speed.
Yeah.
And the tip speed ratio is the ratio of the tangential speed of the tip of the blade to the free stream wind speed. And these are tip speed ratio is a very, very common term, a very widely used parameter in wind turbine aerodynamics. It's a kind of fundamental thing. I'm conscious, David, we may have to move on to another slide if we're going to get through 3 or 4 in 15 minutes. Are you happy?
Yeah, I was going to talk a little bit about wake steering, but I can come back to that later in the Q&A if there's time.
Actually, I know while you're there, because wake steering was something I had not heard of.
Okay. Well, very briefly. So we understand, of course, that the velocity deficit and the turbulence in a wake is really important in the context of a wind farm because it can, A, reduce the amount of energy from the wind farm, and B, increase the fatigue loading. So we need to do something about that. And there are all sorts of wind farm control strategies that are being developed to try and reduce the effect of wake interaction. One of them, really interesting one, is called wake steering, whereby the yaw angle of the rotor on the wind turbine is changed to try and reorientate the downstream wake so that it avoids interaction with the downstream turbine. And this is a fairly new wind farm control strategy that's being researched and, in fact, implemented now on a few prototype wind farms. And the initial results look really good. We're seeing an overall increase in the amount of energy by using this strategy of a few percent, which is really important in the context of the wind farm returns, of course. So that's a very brief overview of wake steering. Maybe we should move on to the...
Okay, well, I think the next one is a different topic, is it? Yes, this is quite a different topic. And I think you posed this question, David.
Yeah, the question is quite a puzzle, really, if you think about it. So if we look back at the history of wind power, there have been two very remarkable trends. First of all, wind turbines have got larger and larger and larger, from maybe 10 or 15 meters diameter in the 1980s up to around about 240, 250 meters now, enormous increase in size. At the same time, the second trend has been that the cost of energy has fallen away really dramatically. So the cost of energy from wind farms is much, much lower than it was 20, 30 years ago. And that's a bit of a puzzle. How can those two trends coexist when, if we think about the famous square cube law, which says that if you take a wind turbine and you increase the size of the rotor, then the amount of energy you get will scale with the swept area, and therefore the diameter squared, whereas the mass and therefore the cost relates more or less to the volume and therefore goes up with the diameter cube. So you would expect, if you follow through that logic, that the turbines would become more expensive, more costly as they grow bigger. So there's something strange going on there, and I'm hoping Colin is going to explain that to you with the graphics he's put on the screen there.
But I think it's pretty well established that there are three kind of main reasons for the amazing reduction in the cost of energy from wind turbines. First of all, the technology, what I've called technology shifts. If you scale a wind turbine design up, it will get heavier and proportionately less economic. But every now and again, if you change something about design in a radical or even a small way, you can get away from that law. So it'll still scale up according to the square cube law, but it'll be on a different curve. And I've tried to illustrate this with the weight of blades that were made by the Airpac, the Dutch blade manufacturer Airpac, for whom I worked about 20 years ago. And their first range of blades started off with something about 10 meters long, and they called them the WPX range. And they scaled the design up to 16 meters, and it followed this roughly cubic curve. As the blade got longer, the blades got heavier according to the scaling law. But round about 1994, 95, Airpac changed the design of the blades quite radically. They changed the thickness of the airfoils, they changed the materials, they changed the layout of the composite structure to optimize its structural efficiency, and they changed the root design. And these blades, for the same length, were about half the weight of the WPX blades. And the new blades, which were called APX, they were scaled up, and they followed, again, the same kind of cubic curve. So they get heavier according to the same law, but they're a lot lighter than they would have been according to the old design. So that's a way in which technology can overcome this scaling law. You sort of subvert the law. And on the right is a very large wind turbine with a 170 meter diameter, 7 megawatt turbine, which shows just how far we have come in scaling up blades. And this one includes carbon in its carbon fiber in the blades, which again takes you to another curve off to the right here. So that's technology shift. Very briefly, the other two kind of key drivers are mass production, or economies of scale, just doing something at a large scale, and very often it gets cheaper because more people are involved, methods get streamlined, new techniques come in for installing offshore, all this kind of stuff. And the third thing is economics. If you accept a lower rate of return on a project, then the energy from it is a lot cheaper. And nowadays we're seeing very low discount rates and very low cost of money for large offshore projects. and this is driving the energy price down to levels that are, in some cases, even lower than onshore wind now. So the short answer, David, I say, is technology shift, economics, and economies of scale. But within that, there's, each of those is a huge area to pick apart. And I'll just come back to that, because the turbine, that 7 megawatt turbine, I understand you actually had a hand in the design of.
Yeah, it's a turbine that's very close to my heart, really. So it is the Samsung Heavy Industries 7 megawatt wind turbine. When I worked at Garda, we had a group of turbine design engineers, and we secured a contract. In fact, it was the biggest design contract we ever had as a company with Samsung to help with the design of this turbine. So we had a major role in the design, working with SSP on the blades, working with Davy Brown on the gearbox, and we supplied the control system actually, and had our engineers commissioning that prototype in Scotland. So it was a great project, quite stressful. I remember, I think I went grey during the course of that project. But the sadness was that shortly after that project finished in 2014, Samsung, at a very senior level in the company, pulled out of wind energy. So they haven't stayed the course, which is a great shame. Anyway, we should move on.
Move on to another slide, see how the time's. We've got time for a couple more. The question here, I don't know if I can quite see that at the top of my screen. Yes, why? I think David asked this question: why is there a trend towards low speed and permanent magnet generators? And in the textbook, I've actually tried to talk about many types of generator, because since wind energy, the modern wind energy industry began, almost every type of electrical generator you can think of has been on a wind turbine, whether it's a standard induction set, synchronous generator, doubly fed induction generators, low speed synchronous generators, permanent magnet generators, the lot. You just about it. It's such a packed field. You kind of wonder, what the rhyme and reason of it is. And I've actually illustrated within the book. There's a couple of illustrations here. One is the difference between a high-speed generator, which requires a gearbox between the wind turbine rotor and the generator, and this case would be an induction set. And here, a low-speed generator with multi-poles, which is connected directly onto the rotor, and this dispenses with the gearbox. And the illustration on the right, which I couldn't resist putting in the book, is a comparison of a multi-pole synchronous generator at the top. And that photograph was taken in 1924. It's from an old electrical engineering textbook. That's from a New York municipal power station. It might have been hydro, I'm not sure. But a low-speed synchronous generator being used almost 100 years ago.
Right.
The bottom, a modern Enercon synchronous multi-pole generator, which is bang up to date. And the difference between them is that the bottom one can be connected to the grid via a solid-state converter, which allows it to be a variable speed wind turbine, which is a huge advance, especially for wind turbines. But the actual electrical architecture of it is really, it's not that new. The generator is a very well tried and tested thing.
Very interesting.
But directs us back to the question, why the trend for gearless permanent magnet generators, especially with large turbines. So I'll put that to you, David. Why do you think that has been there?
Well, I think the main reason is probably fairly clear to most people listening to this call, and it's all about reliability. So over the history of wind turbines, gearboxes have tended to be a source of unreliability. So a number of wind turbine manufacturers have decided to eliminate that problem by moving towards direct drive generators. The jury is still out, though, I would say. If you look at offshore turbines, there isn't really a consensus as yet. So if you take Siemens and GE, they've adopted direct drive. but Vestas and some of the big Chinese manufacturers, Goldwind and Mingyang, have stayed with some form of gearbox with a medium speed generator. So there still isn't really a full consensus on this. It's quite an interesting topic. I mean, the downside of direct drive generators is that they tend to be very big and very heavy. So that needs to be taken into account, of course, in the trade-off.
We're probably almost to 50 minutes up. I'll maybe just put up one more slide, David,
Yep.
and we should give people a chance to ask some questions.
Yeah.
There are a couple here that we were looking at. One about the benefits of variable speed operation. I'll maybe park that. We'll come back to that if anyone has questions about that in the Q&A.
Okay.
This is another one that is much less technical. This is to do with the ownership of wind power, it's a topic. This one's kind of dear to my heart, probably because of my involvement with community projects. But it's something I'm kind of personally interested in because wind energy lends itself to very many ownership models, whether it be, at the scale of the farmer or the small project, business or community, or nowadays the huge offshore schemes. Because a modern offshore wind farm array you're getting on for the same power output as a small nuclear power station. And it's kind of assumed that large offshore wind farms will be owned by large corporations or utilities or even governments. I believe that is not necessarily always the case. And I think there's one well-established example of the Middelgrunden wind farm off Copenhagen, which is partly owned by private shareholders and municipal shareholders in the town. And I think there are now moves afoot to try and get some kind of community or wider stake in even the big wind farms. And David, you told me today about a power company. I don't know if we can name them, but
yeah, no, I think it's public knowledge now, Colin. So I've always thought that community ownership was great for small scale projects involving local people and avoiding any kind of NIMBY attitudes that might exist. But the report I came across recently was in the context of offshore wind farms, and the renewables company Ripple, as part of what's called the Next Gen Consortium, is trying to bring community ownership to offshore wind farms in Scottish waters. It's a new initiative. I think they're just getting going, but it'll be interesting to see how that develops. So I think we need to watch this space really with regard to offshore.
Maybe because up here we didn't get hold of the oil, so now we'll get hold of the wind turbines instead.
Maybe.
That's just we do have more slides, but I think perhaps we ought to turn it over to the Q&A now, to give everyone who wants to come in a chance, and we can always go back if there are questions. Yes, that we have slides for. So at this point, I will open the question and answer session. I might require your help, Ellie, here with feeding questions in either via the chat or the Q&A.
Just while you're doing that, Colin, I see Jaap de Boer has made a comment about reducing rotor thrust within a wind farm on the front turbine to reduce wake effects, and indeed that is a well-used technique and very effective. So I think there are all sorts of different wind farm control strategies that are being explored, and I think wind farm controlling the wind farm as a power station rather than a collection of autonomous machines is definitely the way to go. And I think we're going to see a lot of innovation and development in that area in the future.
If you reduce the thrust, is that a question of with variable pitch, basically pitching down to? Can you reduce the thrust without decreasing your power output? Are there other clever ways of?
Well, I think you will reduce the power output of the front turbine, but of course you are reducing the severity of the velocity deficit in the wake, and therefore the power output of the downstream turbine goes up a little bit. So it's a balance. And if you think about that over the entire wind farm, then you can see that you can potentially increase the overall performance of the wind farm.
I know that I saw that question was from Yap, and I know that he has done a lot of work on optimizing offshore wind farms and looking at them as, yes, beyond just wind farms, but almost spinning reserve, if you like, for the grid. So there's a lot of interesting stuff going on at that scale.
Yeah. I can see some questions now. Colin, have you got them?
Click the Q&A. Oh yes, yep.
So there's one there that I know you and I have talked about previously, and that was the question that came in about what's happening in the States. So.
Oh yes. I'll let you go first on that one. I have my own thoughts about that, but.
Well, I think it's a very interesting question. The first thing I would say is that the Americans are doing quite well anyway, really. So you may or may not know that altogether they've installed about 120 gigawatts of wind power in various states. Last year, I think they installed 17 gigawatts just in the year. So they're doing pretty well. But I think the area that they're trying to take forward that we in Europe know a lot more about, of course, is offshore wind. So they're trying to develop offshore wind off the eastern seaboard and off the west coast of the States. The issue they've got in those two areas is that the water gets pretty deep pretty quickly. So they're looking at floating offshore wind. And again, this is an area that in Europe we're also addressing, and we also have, of course, some prototype of floating wind farms out there already. So that's definitely an area that I think we in Europe can help them with, and there are all sorts of research and commercial collaborations taking place in the context of offshore wind.
Yes, I don't think. Although America has not installed as much offshore wind, I don't think it's a lack of technology, because a lot of the early offshore installations, probably even now, they learned a lot from offshore oil and gas, including spar buoys and things like that. Actually, I'm not so sure about the spar buoy, but TLPs and jackets and so on and so forth.
Yeah,
really came out of the oil and gas industry, and there's not a lot we can teach Americans about offshore.
I remember going to a seminar hosted by NREL maybe 15 years ago on floating offshore wind, and they brought along some of the oil and gas guys who were working in the Gulf of Mexico, and they were putting floating rigs out in about 3,000 meters of water depth. So it was quite astonishing.
But yeah, no, it's definitely spreading, and it's the big worldwide resource, really, floating offshore wind. It's the big prize if the price can come down. There's a few more questions coming in. Should I be looking at the chat or the Q&A here?
I can see a few in the Q&A.
Just have a very quick. Stephen Wilson says he has a non-expert question. Simple explanation for how power depends on diameter and the cube of wind speed. Can I answer that quickly? It depends on the swept area, the square of the diameter, so basically the area the wind's flowing through. And the reason it depends on the cube of the wind speed is that the thrust force at the rotor depends on the square of the wind speed, and power is the product of thrust and velocity, which is wind speed squared times wind speed, which is wind speed cubed. So it's yeah, if you want me to answer that in more detail later, I can catch up with you by email or something.
There's a question here from Joanna Berry, which I don't know whether you can see that, Colin. It asks about the biggest contemporary barriers to more widespread adoption of wind power generation, particularly in the context of COP26 and such like.
The biggest barriers to implementing it.
Yeah, but I think in terms of technology barriers, then I would say that we really need to make some progress with regard to storage, dealing with the ability to store the electrical energy from renewable energy plant when, for example, the wind speeds are are high. So storage is an area that we need to work on, and of course there's a lot going on in that area, both in terms of battery technology, but also hydrogen and other possibilities. I don't know whether you have any thoughts yourself, Colin, with regard to.
Well, the sort of classic answer is cost, but cost is really in the last 5-10 years, the cost of energy from wind seems to be almost tumbling, as it has with solar energy as well, and even more so with solar energy. So it's cost is not, I think, the driver anymore, and we know we need to do these things, and there's always going to be money will become available, you know, as the urgency increases. But the intermittency, yeah, that it's a big one, as David has said, being able to store wind energy so that you don't have to rely on fossil backup. That's the big prize, and that's probably a bigger area of R&D than increasing the output of wind turbines is.
Yeah.
We know we can do wind, but how do we turn it into something that's available all the time, available on tap? Sorry.
Pete Webb has got one here, which we can perhaps deal with fairly quickly. The farm turbine has a small wheel for steering into the wind. How is this done with big turbines?
Okay. I might have a slide that would show that, actually. Hang on. I might have a photograph that would show that. It's done using yaw motors, electric or hydraulic motors up in the nacelle. And I do have a photo somewhere.
So there's usually a wind vane, which is sitting on top of the nacelle of the turbine, which measures the wind direction. And that information is then used to determine whether there is a misalignment between the orientation of the nacelle and the wind direction. If there is, then, as Colin said, there is a control signal sent to yaw motors, either electrical yaw motors or hydraulic yaw motors, that drive the nacelle around. So an angular motion of the nacelle until that misalignment is taken away and the nacelle is pointing into the wind.
Apologize. Oh, here we go. Yeah, hang on. I'll see if I can share my screen on this. This is a photo of the nacelle of an Enercon 44. So this is before it's been put on the top of the tower, obviously, and the generator will get attached to this flange here. But you can see in the floor of the nacelle these two motors. There's another two parked behind. You can't see them. They're electric motors, the little gearbox, and they drive a toothed pinion underneath, and that pinion will drive against a ring on the top of the tower, and the whole thing goes around. It's like the slew ring on a crane, a construction crane. So it's an electromechanical yaw drive, and as David says, the control system is triggered by a measurement from often just a sort of traditional wind vane, but nowadays perhaps from a LiDAR wind sensor.
Yeah.
That photo is in the. I should credit my pal Charlie Robb with that photo. He took a lot of photos when he was installing an E44 on one of the outer aisles, so I have used some of those in the book. Thank you, Charlie. There's a few questions coming up. Have you? That was from Pete.
Yeah.
Gary Page says, driving down the road recently, I passed what looked like a Savonius rotor, perhaps powering a traffic counting device. Is any work being done on vertical axis turbines, in particular for small applications? That's a good question. I am not an authority on that. I know you do see them from time to time. My feeling is you don't see them as much as you used to, vertical axis.
Yeah. Well, it used to be, I mean, back in the 80s, when we were developing the first generation of horizontal axis turbines, there were certainly companies out there producing vertical axis turbine designs. I think they've pretty much died out, certainly at large scale, and I think it's a lot to do with the overall efficiency. If you look at the aerodynamic efficiency of a vertical axis turbine, it's fundamentally going to be significantly lower than the horizontal axis turbine.
I think you may see them at small scale where the efficiency doesn't matter quite
Yeah.
as much, and what matters is that they work in maybe a multi-directional environment or a turbulent environment, but they're not cost effective at big scale, really, are they?
Exactly.
There's a question here from Andrew Want, who says, from your perspectives, are there unique issues or problems associated with floating wind technologies? I was thinking cost. It's not a unique problem, but it is
Yes.
probably the biggest issue with floating wind is it's a lot more expensive than fixed wind.
Yeah, I think that's certainly true. And I think there's a long way to go to optimize the design of the floating foundation structure and its mooring system itself. And there are different solutions for different sites, different water depths, of course. So there are different possibilities, either a tension leg platform or a spar buoy, or maybe a barge with catenary type mooring systems. But cost is a really big issue, as Colin said. I think from the point of view of the wind turbine, there are also some interesting problems. One of which is to do with the motion. Of course, the turbine is sitting on a platform which is moving around due to wave impact, and that motion can itself induce inertial loading, but also can interfere with the behavior of the control system, because you can imagine as the wind turbine is moving forward because of wave action, the pitch controller will try and do something about that and will then interfere with the quality of the power control. So there is a significant control problem that needs to be addressed for floating wind.
It's quite a nice problem, that one. It's the better the tighter the power control, the more you destabilize the rocking motion of the turbine. And I know it's a lot of work that's being done on that, and even suggestions that stall regulated turbines wouldn't have that problem. But you're not going to see big stall regulated turbines offshore. I can predict that.
I think you're probably not going to see big stall regulated turbines, period, anymore, are you, Colin?
Yeah, no, I think they've had their day. See if anything else.
So there's a question here from Joanna Berry. What technological advances do you see powering future developments in wind energy? That's also a very interesting question. I'm not sure we're going to see radical changes in the concept of what a wind turbine looks like in the future. That's maybe a controversial remark, and Colin may have a different view, but I suspect that the sort of three-bladed horizontal axis turbine on a tower sitting on a jacket or a monopile offshore is the concept for taking forward.
It is, although even in the very early days of people thinking about big wind energy, the idea of a two-blade downwind turbine offshore with a very high tip-speed ratio and very flexible blades was often mooted. I haven't heard it much recently, but the idea there was that you could have lighter, more flexible blades because they're bending away from the tower. So
yes,
you can save on material, and I think there were other weight savings, higher speed operation, that kind of thing. Have you heard anyone talking of two-blade downwind offshore?
I think there are still one or two companies that are working on that. I wouldn't be shocked to see that move forward. The other interesting area, I think, is to do with the sheer increase in size. So we've seen in the last couple of years some of the major manufacturers coming out with these enormous turbines, 15 megawatts, 220, 240 meter diameter. Will that continue? Is it likely that we're going to see even larger single rotors on support structures, or will we start to see multiple rotors mounted on the same support structure? I mean, again, there's been some work done in that area. Whether they will come to fruition, I don't know. There is a twin rotor concept that's been developed and installed in the Baltic Sea by a couple of German companies. So
yes, I've seen that. It's quite a sci-fi looking thing, actually. It's
Yeah.
that's a floating device, is it?
Yes, it's a floating device. I think it's called NESI 2. And I think their plan originally was to build a much larger version of the machine, maybe 10 or 15 megawatts in China sometime in the next couple of years. So we'll keep an eye on that one.
Here's one sent in earlier. How do you design a wind farm collector system to minimize cable length? I presume that means how you design a wind farm array so as to minimize cabling between the turbines. I don't know if that is an electrical question to do with optimal circuit arrangements or whether it's an infrastructure question, but maybe put that one to you, David, because I know Garrett Nassan had a lot to do with developing wind farm design software.
Yeah, if it is an electrical question, then I'm afraid I probably can't help you very much. But if it's a more general question about designing the layout and the arrangement of the wind farm, then the standard approach is to optimize the positioning of the wind turbines within a wind farm based on the local wind regime and the topography of the site. And the idea is to optimize or maximize, I should say, the energy yield from the wind farm by moving the turbines to different positions and finding the optimum layout from an energy point of view. And once you've done that, you then take into account other constraints, such as, I don't know, acoustic noise or indeed the length of electrical cabling between the turbines and the local substation, for example. So that there are certainly tried and tested methods for determining the optimum arrangement of the wind farm. But there are also, I'm sure, recommendations for how you should most efficiently design the electrical infrastructure for a wind farm. But I'm afraid I'm not qualified to deal with that question.
I am not really either, but I mean, there are, I know you might have 5 turbines on a ring main where the cables go round them and then back to a collector, and each of them has a ring main unit, so it can be separately disconnected, or they may be radially connected to a central substation. Yeah. But as I say, those come down to serious electrical design, and that's not really my specialty. But I can't remember who asked the question, but if they wanted more detail on that, I'm sure we could point them towards a source. A question here from Pete Webb. Could floating wind turbines be placed inside a caisson to reduce wave motion? That's an interesting thought. And I guess the answer is, I suppose they could, but what would the cost of the caisson be compared with the... because the caisson would have to be high enough to prevent the waves reaching the floating turbine. Yeah,
I can't quite visualize that at the moment. Would that be a caisson that was like a donut that was sitting on the surface of the water, or is it a caisson that's connected in some way to the seabed? I'm not sure how that would work. These floating wind turbines, well, just back up a little bit, bottom-mounted wind turbines, I think, are certainly feasible and cost-effective in water depths up to about 40 meters, 45 meters maybe. Once you get above that depth, so 50, 60 meters, then it becomes pretty expensive to build a jacket or a monopile structure. So then floating wind becomes much more attractive. So if you're sitting in a minimum of 60 meters of water, then I think it would be quite expensive to develop a caisson for reducing wave motion.
I think bringing down the cost of floating offshore wind is definitely one of the big prizes, and it's not obvious how it can be done. Because you need such a large ballasted but buoyant mass under the water to hold the structure above it.
It's a tough challenge, but the prize is enormous. I think the resource that's available if we can go to deeper water is enormous, of course. So I think the industry will get there in the same way that the industry has managed to reduce the cost of bottom-mounted offshore wind so dramatically in the last, well, relatively short period of time, actually, over the last 5 to 7 years.
Actually, I'll just go back to Pete Webb's question, and maybe you said this when I was scrolling here, but if you have a floating wind turbine on a spar buoy, the dimensions of the spar buoy are actually chosen not to react to the wave motion. So if you see a turbine on a spar buoy in the sea, it's remarkably static. I mean,
Yes.
it does pitch around a bit, but not nearly as much as a ship would. You look at it and you think, oh, that's pretty stable, really. And it's because the wavelength of the sea waves is so long compared with the tenderness of the spar that it doesn't respond. And I think, again, that's probably something that came out of the oil industry. That's kind of a lot of hydrodynamic research behind that.
I think the spar buoys, though, are for relatively sizable wind turbines are pretty large, aren't they? So they're of the order of maybe 80, 90 meters in length, I think. So you need to have a pretty deep water site to make that cost effective, of course.
Yeah. Did we have some more questions? There's another one from Yap de Boer. Forecasting output power is increasingly important. What approaches in wind turbine or wind farm design could you think of to improve this forecasting? If Yap's still there, do you mean forecasting a few minutes ahead or seconds ahead, or do you mean hours ahead? Is this for? Maybe if you want to answer that while I'm thinking about the question. In the very short term, I'm thinking sort of LiDAR gives you a better wind sensing measurement into a wind farm than anemometers, but that's not really. I think that's possibly not the answer you mean.
I mean, forecasting in terms of hours ahead is already done. Of course, it's done for trading purposes. It's done also for scheduling maintenance visits to wind farms and such like. And I think there are a number of software packages out there that rely on SCADA data from the wind farm as well as local Met Office predictions of weather patterns to be able to produce those forecasts day ahead. And so, so I think that kind of technique is happening already. What approaches could improve this? That's a good question. I'm
not a meteorologist. The parts of the book that deal with meteorology are at a fairly simple level for wind farm installation and so forth. But I guess satellite technology. Well, satellite technology is very much used for weather forecasting now. I presume that includes wind forecasting.
Yeah.
And whether you could get better than that, I don't really know. And
no, I must say, I thought it was already pretty sophisticated, the kind of forecasting that was being used out there already. But I think I am somewhat ignorant of what's going on.
An interesting question, actually, I'll maybe ask Yap this sometime offline, is if your forecasting does become much better, how much can that improve your overall grid management? What is the prize for better forecasting? Does it allow you to operate wind farms more effectively? Because at the moment, wind farms they're operated when the wind's there and not otherwise. But if you could forecast the wind better ahead, how much can you gain in the overall operation of your grid? But that's, sort of extending the question a little bit there.
There's a question here, Colin. What do you see as the two most distant specialist areas in wind energy, and how does your textbook help to bring these together?
Is that distant or distinct, do you think? Is that?
It says distant. Yeah, it's a tricky one to answer, but I again, if we're talking technology, then the various specialist areas actually are pretty highly coupled for a wind turbine. So if you think about the meteorology and the aerodynamics and the structural dynamics and the control system, all those different specialist areas are highly coupled. So they're all pretty important working together. I think it's interesting, particularly how control through software and sensors and actuators has such a big influence potentially on the structure of a wind turbine. If you take a blade, the amount of structure, the amount of material depends highly on the loading, of course, that the blade experiences, and that in turn depends crucially on what control action the turbine is taking. And that also then takes you into all sorts of interesting areas such as aeroelastic tailoring, where the shape of the blade may change for passive control purposes, the use of memory materials and so on. So I think there's a lot of interesting areas there that
yeah, I think one of the early lessons, and I remember we were both involved in this, David, with different companies, was how pitch control on wind turbines influences the fatigue life on the blades. And in fact, better control sometimes meant more fatigue, and there's a trade-off there. So yeah, it's almost, coming back to the questioner, it's almost impossible to separate out aerodynamics from control from drivetrain design. It's, yeah, wind turbines are it's a very integrated kind of system.
Right. Where else?
Can I say we've answered that question? I was a little bit vague at the end there, but it does. In terms of the textbook, what I hoped to do in the textbook was go through it in such a way that each chapter kind of built on the ones before, so that by the time I was talking about control, we'd already looked at generators and aerodynamics and how those things tie together when you come to a very sophisticated control system like a variable speed, variable pitch wind turbine. So how does my textbook? Well, I'd have to ask anyone who's read it whether it helps, rather than me say how it helps. But hopefully it's a sort of sequential explanation of how a wind turbine works.
A nice question for you there, Colin. Nice, easy one. What was your favourite chapter of the book to write? Do you have a favourite chapter?
Well, actually, yeah, that's not an easy question. I could say the final one because that meant I was finished. I think it was possibly to write. It might be the introduction, or it might have been the final chapter, because the less technical chapters allowed me to be a bit more expansive. You know, a little bit more kind of subjective rather than objective. And it's quite nice when you're writing to give a little bit more kind of free thought. But no, they're all a challenge in different ways. Yeah.
Right.
We have one at Pete Webb again. Whether it's a complex system, there will be an upper limit to the efficiency of forecasts. This is probably an answer to the previous question. We might be there already. More sensible would be work on harvesting the energy during the good times. Yes, here. Harvesting and storing, I think, is the answer.
Yeah, absolutely. What are the most significant engineering challenges involved in wind design and installation? Well, we could probably talk for another hour about that. I think we've covered some of them already. In my mind, at least, I see the challenges of developing cost-effective floating wind as being significant, certainly, and really important for the future. So that's one area. I also see fantastic potential yet for really smart control on wind farms, as I mentioned earlier on. I think there's a lot further we can go with the use of big data from many sensors across the wind farm in an intelligent way to drive the control system.
Yes. In terms of installing wind turbines, I think one of the biggest challenges is probably the management of it. You can have a rotor on the ground, it's about to be lifted up to complete a construction that's taken 4 or 5 days, and then the wind gets up, so it's not safe for the crane, and you have to wait 2 weeks for the wind to drop. So I think the challenge isn't just the engineering, it's the organization and the management of installing wind turbines that can be as difficult and as stressful as the actual engineering.
Yes.
The engineering is something we've actually become very good at. The management part will always be a challenge one way or another.
So there's a comment from Yap. It's a comment or a question. It's got a question mark at the end of it from Yap at the bottom there. Lower power capacity, no straight lines in wind farms. Do you understand what Yap's driving at there?
If you're still there, Yap, are you suggesting that if a wind farm has no straight lines, you could get a higher? If you're optimizing a wind farm layout for maximum energy, but a maximum amount of stress or whatever, will you end up with a non-linear array, basically? Not an old-fashioned grid, but a kind of more. I don't know the answer to that because I haven't done a lot of wind farm design or optimization. David, you might have.
Well, I think wind farms that have regular grid arrangements, in other words, lots of straight lines, are obviously attractive in flat terrain, such as in northern Europe. But as soon as you go to undulating terrain, such as we have in, for example, many parts of the UK, then we don't have straight lines anyway. The turbines are located to provide the optimum energy based on the topography at the site. So I think straight lines in wind farms, I suppose offshore, yeah, you tend to get a lot more straight lines. That's certainly true. Now, typically the wake effects, the wake has decayed by around 7 to 10 diameters downstream of a wind turbine. So if you keep the rows of wind turbines that far apart, then the wake losses and the increase in fatigue loading due to wakes becomes less of an issue. But then, of course, there is a cost trade-off. If you have the turbines further apart, then you've got more cost in the electrical system infrastructure.
Hey, I've just seen a message, I think, from Ellie, just politely pointing out that we have come to the end of our time. I think we're a minute away. So I think at this point, yes, I'm going to have to wrap up. It's a shame because yes, I'm sure we could have carried on indefinitely. But yeah, can I just say thanks to everyone who has sent in questions, and thanks to David.